Hello.
Yeah, can you hear me?
I can hear you with poor quality.
Poor quality. Okay.
It's getting better now. Yeah.
Okay. Yeah, my AirPods gave up, and then it takes a bit of getting the system to recognize it again. But all right, you're ready, I hope.
Yeah, I'm ready. Can you see my screen?
I can see your screen. I can hear you.
Very good.
I can see the slides. Yeah. And you shared the entire screen. Yeah.
Yeah. This is on purpose. I'm planning to do minor demo.
Good. I can also turn on my screen. I can see your code. Hi, Richard.
Hi, I can hear sort of like a weird kind of heartbeat sound coming from
Yeah,
someone.
me too. Me too. I'm not sure where that comes from.
Maybe it's because my mic is on my chest.
I don't think so. No, I don't think it's an actual heartbeat. I think it's some
No.
sort of digital fragment of some sort.
Yeah.
Okay. Well, maybe it's due to the silence.
I'll mute myself to see if it.
No, I can still hear it. I think it's coming somehow from Jean-Philippe's setup. There may not be anything to do about it. It's not so bad.
No, I don't think I can do anything about it. In fact, I could try to improve it, but it might just make everything worse. I think this is what it should be. I think when I start talking, it will be better because the system picks up on silence.
So before you start, Jean-Philippe, I have a small announcement to make to people here. So Rudy Matela suggested that maybe you've looked at the final session of today. There are 3 slots. 2 of the slots are taken up by research papers, and I had to kind of allocate the 3rd slot. Otherwise, the speakers would thought they had 45 minutes. So this is like a bogus slot. And now Rudy Matera suggested that we could do lightning talks in that particular final slot. So if you want to take advantage of that and spend 5, maybe 10 minutes on something related to Haskell, then you can send me a message and I'll see if what we can fit in. So that's all the announcements I want to make. So send me a message privately through AirMeet. Well, without further ado, I'm going to announce the invited speaker for today. So yesterday we already had a large piece of linear Haskell, and you're gonna get another dose today. But now from Jean-Philippe Bernardi from the University of Gothenburg, we'll be talking about linear Haskell today and tomorrow. Go ahead.
Thanks for the introduction. Yes, indeed. So that seems to be the year of linear types in Haskell. I have planned this. So I'm first going to talk about, do a summary of what you can do today with GHC, with the linear types as implemented. And the second part will be about what I think could be the future, hopefully to inspire future research or discourage, maybe. We'll see. Hopefully inspire. Okay, so before we get into before we get into all that, let's just remind a little bit, in a few words, what linear types are about. So I'm sure all of you are familiar with the regular arrow type. So this type declaration here expresses that f is a function that produces b, or a value of type b, using a value of type a. And you have the linear arrow, which is written so traditionally with a circle. And this only adds an annotation about quantities. So to get out 1b, f consumes 1 or exactly 1. You could, here by 1 I mean exactly 1. 1a. So f produces exactly 1b using exactly 1a. And that's all there is to it. You can stop listening now. So, no, joking aside, let's see what GHC can do today. So perhaps some of you haven't haven't had the chance to experiment with GHC 9, which has linear types. So a quick demo. So you can use so the non-Unicode. I'm activating Unicode syntax because the non-Unicode syntax is pretty poor, as you can see down here, in my opinion, anyway. So we can declare the identity function, and well, I'm sure everyone is familiar with the identity function, and because it actually produces one output using one input, it can be assigned a linear type, and so here it is. So GHC checks the type here, and you can extract the type, and GHC pretty prints it like so. And this is another notation from the linear arrow. And here, this is the number of times that this argument is being used, and in this case, it's 1. It can also be written in all letters with a capital O. That's a type, essentially. Okay, and so does GHC actually checks that? Well, here you go. So if we examine here what GHC says about this forget function, if I attempt to not use x, GHC will come with this kind of error. So it says, well, you try to use x many times, whereas you declare it to be one time. And many really means any time, any number of time, or whatever, or something like that. But the identifier any was already used, so implementers have resorted to many. So let's fix all errors. I could write x, but that's not the right type. And likewise, you cannot duplicate. So if you declare that you're going to use x exactly once, you cannot produce a result which where x appears 2 times. So that's also checked by the compiler. But let's fix the error maybe like this. This is no longer the duplicate function, so let's delete that. And so so in sum, exactly once is a special case of many. So really, whatever, any number of times. So in particular, every linear function is also your good old function. So we can convert a linear function into a good old function. And here I'm also using the Unicode syntax. So here it is, the implementation is as simple as you can imagine. Well, actually, if you try to do this, it's not going to work. So there is no subtyping between this and that, but there is implicit conversion between the multiplicities here and that. Okay. And the other thing doesn't work. So any old function is not a linear function. So that's also an error. This I told you earlier. If you want to force this many multiplicity in a data type, you can by just using the linear arrow, the nonlinear arrow, sorry. So here it is. So this UR is pronounced unrestricted. So unrestricted A, well, this is how you put this A in a box so that even in a linear context, you will have an unrestricted number of A's there. So that means that unrestricted times A linearly to B. So exactly one unrestricted A, that's the same thing or isomorphic to the good old usual arrow. So here is the conversion in one direction, we just wrap, and the conversion in the other direction, we unwrap. Okay, here I was a little bit lazy. So exercise, do the projection from here. Okay, so what about branches? Well, so it seems that here you have to write X one time to satisfy the type checker. So you have to do the same in every branch in reality. So so if we try to do this, this doesn't work because in the false branch we are not using X. I can also just not write this branch at all, and then we just have a warning. Well, the usual warning that we didn't define the branch. So this may be surprising. Linearity seems not to be checked. Well, this is a normal thing. So in Haskell, you can always satisfy the type checker by crashing. So this is the same with linear types. So this is only, linear types give you only a static property. And so be careful not to introduce magical properties to linear types. These are just types, nothing more. Okay, let's see now. Oops, here is the talk. Here are the slides. And so, okay, let's address immediately the elephant in the room. There had been other functional languages with uniqueness types, like clean, etc., and a lot of research on it. So why didn't we use that? Why did we go for this? And well, the answer is, as far as I can see anyway, Haskell is very much inspired by this Curie-Howard connection. So there is a correspondence between Haskell and second-order intuitionistic logic. And so our idea was, well, let's just draw on this correspondence and transport whatever exists in linear logic, and we're going to obtain linear Haskell. So as far as I can see, this is the principled way. I would argue the most principled way to go about this problem, and this way we can get a lot of research that we can apply. Not everything, maybe, because there are lots of variants of linear logic, but hopefully a lot. Okay, so, but then can you really do unique values with linear types? Okay, well, let's try to convince ourselves that this is possible. So this is in the original, the 2019 paper on linear Haskell. Okay, I redefine everything here. So this is the new thing. So how do you make a new unique object? So here is the design pattern. So we want to make a unique object here, and the way to do that is to use a sort of a double negation system here, where this arrow is linear. And so inside the continuation here, you're going to be given a single copy. And the reason why this is the right way to go is the continuation returns an unrestricted amount of A. And so it doesn't matter if this is called, if we need one A or if we need many A's, whatever, we're going to always get many A's. And so this means that to the continuation, it's always valid to give a single copy. And this single copy is going to be to remain a single copy as long as every function in the API that manipulates these objects preserves the quantity. So, for example, you have this type of signatures when you produce one object using another object, but well, it could be any other type as long as the quantity of objects are preserved. Notice, by the way, that the pairs are linear as well when you activate linear types. So that would be a quantity preserving function here. So let's go back to what we. Okay. All right. So what else do we have? Okay. So a big question is, if you introduce linear types, aren't you going to have a problem, because many functions can be either linear or unrestricted. So that means that you will have to create a different version of all these functions, and because these functions can be used by other functions, you're going to get a combinatorial explosion. Well, this is a legitimate concern, and we addressed it in linear Haskell by polymorphism. Okay, the usual answer to every problem in type system. Okay, so let's see how this plays out. So, okay, I'm hiding the usual map function, so I can redefine it. So this is how it would be defined naively in Haskell. I mean, it's a correct implementation, but GHC does other tricks that we don't really care about here. So, empty list becomes empty list. The cons becomes a recursive call in the tail, and apply f in the head. Very well. And so we see that the linearity of the list here is preserved. So every element is used exactly once to produce exactly one result. So we can also, keeping the exact same code here, we can give it a linear type. Okay. So if the input function is linear, then the output function is linear as well. So, okay, so how we said polymorphism should do the trick. So how does it look like? Well, there it is. So here is the polymorphic list map function. So we quantify not only over the types A and B, but also on the multiplicity, which I call P here. So this means that this generalizes these two functions by generalizing on this arrow and on that arrow. And so here is what you get. This is how it reads. So to produce exactly one B, you need P times A. And, well, this is the reading of this particular type. And the reading of this arrow is to produce exactly one list of B, you need P times the list of A. And the definition remains the same. Oops. And in particular, you're getting instantiation like so. And here it's implicit. So like type application usually don't have. So this is nice. And well, okay, so this is, I became lazy here and I didn't. This is the same as this. Okay, there you go. It loads. Just to let you know, this is live GHC. So if I put here this, you can see that the GHC actually checks multiplicities. This works today. Okay. So here we are. So that works. Very good. So In sum, you have it, it works, and what can we do with that? Matthew gave us yesterday an overview of high-level things we could do, and these are actually addressed in this 2019 paper. So we develop unique references, like I shown earlier, but well, developed in a lot more detail, and bindings for foreign stateful APIs, which is what Mathieu was most concerned about yesterday. In case you missed the talk, I think it should be available somewhere on the conference website. So come back to these 4 details, or even better, read the paper. Well, if you have more time, you can read the paper. And well, this year we have more contributions in the Haskell Symposium. So both of these papers give us more applications. So in particular, session types. In fact, session types with priorities will be presented in a few minutes. This is the next talk. And after that, we will talk about symmetric monoidal categories. So I'm not going to get into details here, but everything that you can do in a symmetric monoidal category, you can represent it using a nice lambda function in linear Haskell. And all this you can do today. It will be type checked, and multiplicities will be checked, and so you will have this nice sense of safety that things work and are safe by construction. Another thing which is very important, I'm going to start with this. So the implementation effort, even though I'm giving the talk, the implementation effort wasn't, I didn't take part in this. We have to thank, Arnaud led the implementation effort, and a lot of work. Probably even more work was done by Christophe and Mathieu. And so, already in JT 0.0, so released all sets of packages compiled with it, so go ahead and use it. And if you're wondering how to, if you don't want to redefine, let's say, linear maps, etc., the linear version of the map function, check out the linear base, which is an extension or a replacement for the, well, let's say just a base library for linear types. So all that is available for you right now. Okay, so that was it for this part. A little interlude. So let's come back to, so that I can explain to you research directions which I envision. Let's come back to the seminal paper, why functional programming matters. And so I don't think I make a big mistake if I paraphrase it this way. So John Hughes is arguing that in Haskell, so in any functional programming language with the lazy evaluation, the composition G after F is a powerful thing. And the main reason for this is because the glue is powerful. And as far as I can see, when you read the argumentation, the glue is really this type B in between here, which is very powerful. So let's say in Haskell, and John Hughes uses this example extensively. What if you have a list of something, doesn't matter what, I wrote alpha here. If you have a list there, well, I mean, this is nice because this kind of, this composition kind of behaves like a conveyor belt. So you can have here a function which is in charge of making a series of approximation of a numerical function. So you get to more and more precise results as f runs. And here in G, you're going to, let's say, filter these approximations, find one which is sufficiently close to the result that you like. So you have more ways to structure your programs. And this is thanks to restriction in the language, which makes composition always safe and easy to understand. Okay. There is, though, a slight problem with this picture. So a lot of examples use this case where these well, not the arrows, in fact, but rather the circles, they are like pipes. So in the sense that whatever comes in, comes out. A lot of examples are like this. But it turns out that, of course, this is completely wrong because the function g can use its argument any number of times. Let's imagine g uses its argument 2 times. Well, then you have 2 possible implementations for the composition. Either you run f 2 times, so you get well, you get your 2 copies of b by running f twice, or you run f, you make a copy. Okay, so you run f and then you save the result, and then like this you can use it twice. And so you have 2 different kinds of behavior, and depending on whatever the compiler decided to do, you're going to get different runtime behavior. And this makes it very hard to reason about performance. I think in terms of the previous talk, this is unstable, so even. So if you make a small change, you can switch to one behavior to the other without realizing it. And well, that makes it, this is a big part, I think, of why Haskell has this reputation as surprising performance. And so, well, I mean, linear types restored a simple picture, right? Okay, so we get, if we extract one C here, while we are sure that if this one is linear, we're sure we're going to get to need exactly one B, and so then it becomes easy to reason about performance again, about runtime behavior in general. So I think, to me, if I had to sum up why linear types matter by direct reference to the seminal paper, I think this is how I would sum it up. So hopefully this is a nugget of information that you can remember. So there is just a little bit of a problem, is that I think even though, yes, the picture is restored, it's still hard to know if what's going to happen in reality, even in the presence of linear types. So the situation, from a practical point of view, there are lots of optimizations in GHC, and a lot of these optimizations depend on multiplicity of functions. And so the compiler today computes these multiplicities, but these analyses are only approximations, conservative approximations. And the reason why this is difficult to do is because of recursion and, well, maybe module boundaries and things like that. And so, the behavior of the program depends on this complex analysis, and so in consequence, the runtime behavior can be difficult to predict by the programmer, because they would have to, every time they make a change, to run in their head the analysis, and sometimes, well, this can fail. I mean, the programmer's reasoning can fail. So one possible path, one possible research direction, I think it would be to make sure that GHC has consistent predicate and predictable behavior by using these, by taking advantage of these linearity declarations. And also, well, I think all the other goodies are there in GHC, so I think this is ready for the taking. So this way, if all of this is done, then it means that the programmer can declare a linear type, and just this typing declaration would ensure more predictable behavior at one time. So I think this would be, this is not started. If you're interested, I think this is up for taking, if you think this is a meaningful idea. Now, second thing, improve the runtime behavior. So today, linear Haskell is just in the type system. And so for Mathieu, this is satisfying because, I mean, it's sufficient because, all these linear functions will resort to calls to the FFI, so it doesn't really matter what if the implementation is efficient or not. But so this is linear Haskell is only in a type system, and so don't think that anything clever is done. So, for example, let's go back to our example here. So here I said, well, look here, this is going to be a unique object. And so if you implement this with FFI, that means that this one here can be implemented using the FFI by a mutable update or anything you like. However, if you implement this object type within Haskell, the runtime system is going to be exactly the same. So this is going to be allocated on the heap. Maybe like this, okay? So we have this. I made a trivial implementation here. The object type could be something like that. I mean, obviously that would be something more complex, but for the sake of the discussion. So that would create an object, and this object would be allocated on the heap today. Likewise, a function that manipulates the object here, it would behave exactly the same as before. Now this is just the identity function, so it doesn't matter, but you can imagine it can be anything, something a lot more complex. And so this will be allocated on the heap, and this will be implemented by allocating more closures on the heap, probably, in practice. That seems a bit wasteful. So here, if the object type is abstract, so not exported by the module, the compiler could prove that unicity is preserved and could potentially provide more efficient implementations. So not using the garbage collected heap here, and this could be even an in-place update and things like that. So this could be done. And I think what's funny, or at least when I read Gerard's paper from 1986, where he proposes linear logic, I think he's already suggesting that this could be used for an efficient programming language. But we haven't done that, and we don't even have a clear plan yet. So this is right? Hopefully a topic of research for some of the people at the Haskell Symposium. Okay, third thing. We have multiplicities. And multiplicities are, well, they exist already, and they are quite powerful on their own. So they form, well, they almost form a ring. So we have this one thing, we have a notion of multiplication, we have a notion of addition. And that seems that that would seem only natural to complete the structure and add a zero identity element. And if you look at a lot of type systems, they are special cases of, let's call it linear Haskell, plus a zero and a notion of subtyping for multiplicities. So formally, this can be an order or similarities on the multiplicities. And this gives a general notion of modalities that could be used for a lot of things. So seemingly with just a little bit more stuff, we could do at least all these things. So not just linear, but affine, relevant type systems, so all kinds of substructural type systems. We could count things a lot more precisely, not just exactly once and whatever many, but maybe one, exactly two, one or two, 0, 1 or 2, 0 to 5, etc., etc. So that could be used very useful in certain contexts. So there are, in fact, there is a lot of research that defines and takes advantage of such systems for practical purposes. These modalities or these multiplicities become modalities, can be used as capabilities, for example, for information flow security. Yesterday, there was a talk on graded monads. So instead of using an explicit monadic structure with the grade, you can use the multiplicity in arrows to represent the grade. So throw away monads. In a lot of cases, you don't really need the monad. You just need a modality. So real numbers fit this structure. And so if you really want very precise quantities, for example, for differential privacy type systems, well, there you go. You could use that. There is a notion of irrelevance, which is important in dependency type programming. Well, Haskell is moving in this direction, so who knows? That can be very useful for irrelevant arguments. The zero modality can be used for that. And in reality, arbitrary effects can be associated with these modalities, in fact, co-effects. And so this is a very general, it becomes a very general device to express things within the type system. So this, I looked at it with Andreas Abel, and you can look at the paper ICFP last year. It's titled Unified View of Modalities in Type Systems. So, and in some way, it's a small extension of linear Haskell. Okay, oops. Yeah, no. So, be careful. This is the, so in that paper we looked at the type system itself, but in practice it's going to make type inference, well, probably the programmer needs to add a lot of type annotations, and the problem is it's not clear. The design is not obvious, don't hold your breath for GHC. But I'd like to work on that. So in conclusion, what I would say is this was a good choice, a good design, if I may say so myself, because multiplicities give you a lot for a relatively small cost. Okay? So yes, we had to change the arrow type in GHC. So that's, well, you can imagine that this touches a lot of places in the compiler, but even for a very mature system like GHC, it could be done. It passed all the roadblocks and it's within the compiler. So in some sense, this is already paid for you. And you can do a lot of things. So all these stateful APIs that Mathieu talked about yesterday, protocols, session types that we're going to see a bit later today, symmetric monoidal categories that comes afterwards. And I'm hoping that, so without touching the type system, but with, not more work on GHC, we could have just faster programs using just linear types. So what I mean by this is just change the type annotations and your programs become faster. More control on runtime behavior. This is partially today as well. Okay, if you declare a function linear, the user of the function will know better what the function does. And these more expressive types, well, this is what I mean by this. All these things that are in the literature, you can import them. Sometimes exactly, sometimes with a small difference. Okay. And I see I have like 5 minutes left, so I don't know if I should be interrupted, but I don't see any catastrophic thing. So I think what I'm going to do in these 5 minutes is to show you. So the next talk will be on quite complicated session types, but I want to show you how linear types help you do these protocols. So let's dive into some code a little bit. So in fact, you can do protocols today, so to speak. So if you have an ambient type of fx, which I call f here, a lot of times it will be just IO. You can represent a protocol which, let's say, so in this example, we take one query and there is a reply, and another query and a final reply before we stop. Well, you can do it like this, okay? So if you have a server that follows this protocol, we can write a program that uses it by, well, calling the server one time with the first query. I'll just call it Q1 here. Then the server comes, you have to be not afraid of continuations. So if you're not afraid of continuations, you just use this. So the server comes back with the reply, R1, and a callback to continue the protocol. So we can maybe do some more things and then call back into the server, and we send the Q2, and the server comes back with the second reply, still in continuation passing style. And finally, we are we are done with this protocol, and we can continue doing whatever we want with these two replies that the server gave. Well, that's all well and good. The issue here is that this callback function could be called several times. And that would mean that the protocol has to be reentrant, or the server has to be reentrant. So every time you're in the middle of conversation, you can either drop the conversation right there, or save this, save the point in the conversation you were, and come back to that point in the conversation. And this is usually not what it wants, even though sometimes it is. And so, well, how do linear types help? Well, I mean, let's just make sure that these continuations can be only called once. And so, okay, that's it. Maybe you don't see the difference even because it's so small. So let me try to line things up. If I may. Maybe I can. There you go. So if you look carefully on here, the points become a circle, and that's it. This is your linear. This is your poor man session type right there. And so there is a slight difference here as well. That the continuation combinator cannot be just that. It has to be a little more complicated. Right. This. So I would say this is a rather small. Well, it's one way to get started with the session types or protocols that you can do today very simply, as long as you're comfortable with continuations. That gets you there. So I think this is another example of getting a load for a small cost, even though I think in a few minutes we're going to have an example of a much more powerful library to do session types using, still leveraging linear types. So stay tuned for that. And I think I'm done now. We'll relinquish.
All right. Thank you for your presentation.
Thanks a lot.
There were a number of questions already lined up for you, so I'm going to show them on stage, and also in this case invite to the stage the person who asked the question. We have a bit more time in this case.
Oh, this is an excellent question. So I think it means
we have to read out the question, because otherwise the YouTube people can't follow it. They can't see the question.
Ah.
So
do you want to do it?
Yeah, I think, can you pose the question?
I can pose the question.
Yeah, sure. There was an example of MK unique or make unique in the talk, and I wasn't sure why you need UR in the continuation.
Absolutely. So can I recover presentation mode? As long as the question is shown, apparently I cannot. I don't
think so. I'll remove the question from the stage. Can I? I can take this away, I think, and then you can reshare your screen and show the slide.
Yep. Okay, so here is the situation, and if I understood the question correctly, you're going to. It's just what if we had removed this thing here?
Exactly.
So what if we remove this thing here? Well, so in this case, the continuation produces just one A. And so that would be, of course, I mean, this is fine as a type, but now, if someone, there is a caller to MK unique itself, okay? And if the caller to MK unique needs just one A, then this type would be fine. We would only need one object. But it can happen that MK unique is called in a context where someone wants many A's, or a ton of A's. And if it needs a ton of A's, well, we need to call the continuation a ton of times to get a ton of A's, because the continuation produces only one A. So if we want a ton of a ton of A's from one object, then we have to put this box around it. Yeah, this is unrestricted. So we want a ton of A's, or an unknown. We want to be able to get an unknown numbers, and this is how it's done. Is this answering the question?
Yep. Thank you.
Okay. Thanks a lot for your question. In the implementation, are there any interesting... Okay, I don't know if the questioner wants to ask the question themselves. I think, Jorian, you're muted. And the question is...
Yeah. No, he cannot. Oh, he cannot be invited to the stage.
Okay, it's popping in and out of existence, so we can just read the question. Yeah. In the implementation, are there any interesting interactions between linear types and core transformations? For example, a need to ensure that a value doesn't get duplicated during optimization. Yes. So we need the core. I think the first thing to say is we need the core. So the core is the internal representations that GHC is using, and this should be linearly typed. Otherwise, we can make mistakes, and so I don't know if this was achieved 100%. I think 99.999 or something. But the core-to-core transformations had to be linearity preserving, were made to be linearity preserving during the course of the implementation. And I think this has even uncovered some bugs, or at least some, interestingly complicated design, let's say. I can't remember any of it from the top of my head, unfortunately, but the answer is yes. This should be answered by the implementation guys like Arno or Christophe.
Okay, so I marked this as answered, but there's another question by the same person who just wants to see this confirmed. So is there a way to express at most one usage in the current implementation? In his understanding, this is no, but...
Well, I mean, so there is a way, but it's not very convenient. So if you quantify over a modality, this modality can represent anything you like, or if you quantify over a multiplicity, okay? So you say for all Q, and then you make sure that this Q is convertible to whatever you, well, if you have Q times alpha, you want it to be convertible to at most once. The thing is, this notion of at most once would have to be part of your API as well, because the native pattern matching, let's say, uses the notion of one time or things like this. And so, yeah, so you have to do the explicit conversions yourself. I think this would be the upshot there. So currently, no, and I mean, yes, but it's extremely inconvenient. And so what you need is the extension that I talked about in the second part of the talk. That would be, so there you define the addition and the multiplication to mean what you want, and from there you can, you have what you have. This is called a fine type system, I think.
Okay, thanks. I don't see any other questions, so I think I'm at liberty to ask a question myself. So this relates back to, I think, what you just talked about. So when you talk about using linear types for optimization, then I think you would like to have affine types, wouldn't you? Because if I say I want to create something and I know that if I know it is used exactly once, then that's fine, and the compiler could take advantage. But maybe it could also be used 0 times, and then I still would like to be able to say and that doesn't change anything, at least not in terms of being able to destructively update the value, for example. Would you agree?
Well, it depends what kind of optimization you want, right? So some optimizations will want that, but let's say I think if you have linearity, this would help you trigger things like you don't even have to do a deallocation, for example, in certain cases. So both are useful.
Okay, so there's another question from Gergo. I'll show him on stage.
Could you
It's
have?
very difficult to read this out, I think.
Yeah, but I mean, the answer is yes. Yeah, I mean, yeah. I mean, this is so the question is, I think the question actually, so there are several ways to oh yeah, we have to read this for the YouTube people, right?
Yeah.
I don't think we can read that, so we have to do by hand. So again, if you give me the if you hide the question, I will explain.
Yeah, give you the screen back so you can share.
Okay, I have to remember to share. There we go. It's a little bit fuzzy. Here you are. Okay. So the question is, can we have this? And there are several ways to understand this question. Is this a subtype of the actual dollar, which is something else? And I think the answer of that is no, it's not a subtype. Another question is, can you define this? Well, I think the answer to that is yes. If I define it correctly. There you go. So we can define it. And okay. Finally, another interpretation of the question is this a suitable implementation for what's below here? Well, let's give it a try. Okay, so we have errors due to this, but those are fine. And so the answer of that is yes. And finally, can we just use it directly here? And this I don't know, I will have to try. And I think the answer to that is yes. So I think that was all I could think about this question. Of course.
Maybe for myself,
yes.
Does that mean you cannot use $... to replace the old dollar? Is that?
Well, what is the old dollar? Well, we can. I mean, we can try in this context, and in this context, I think that will work. Yeah, that does definitely work in this context. The actual dollar is something which is
A to B to A to B?
This is, I think, what most people think. And in this case, I think that does not exactly work because it has to be expanded at least, and that works. So I think this, yeah, I actually misread that at first. But it's yeah, that works. So that would be the case. I think there is nowadays an extra special thing going on, and I think this extra special thing is about to be removed, if I remember correctly, in GHC, but yeah. I think now we have exhausted the question. Thanks to you.
Okay, I'll mark this as answered. I think this also answers, I think, the next question of Gergo, but let's check.
There is one raised hand. Oh no, he's raising his hand now, Gergo. But
right.
maybe
So I'll just give him the mic and then he can clarify and then we can conclude the session.
Yeah, so
Gergo,
I guess my real question is whether you could define a single dollar with the type from my previous question, and it seemed like after Urian's follow-up question, it seemed that the answer was yes. But then, of course, there's also the fact that dollar is wired into GHC, and there's all kinds of extra special magic going on to support basically higher rank applications of it, right? So that you can do run st dollar something. So, but I guess my question is whether all of that is orthogonal to the linear types work, and whether all that would just work if we changed dollar to be that single multiplicity polymorphic version.
I mean, I would love to tell you just yes, right, for everything. So the extra special thing for run st is about to go away, if I understand the state of the art.
I think 9.2 it will be gone, so there's no special hack anymore for dollar.
Okay, and then when it comes to, I mean, there is a practical question: is in certain cases, maybe this isn't going to be, you know, like maybe the P won't be inferable, and that's going to be annoying for the programmer. And this is very hard to tell you like on the spot.
Okay, I guess all of this was just motivated with just me not liking the worth of having to have a different dollar operator just for linear application. So it seems like we don't. So that's cool. Okay,
Excellent.
thanks.
Okay,
Yeah,
great.
Yeah. Thanks a lot for the question.
I'll kindly remove you from the stage and mark this as answered. So going back, all the questions have been answered, and it's exactly 4 o'clock. So I think this is time to thank the invited speaker for his presentation and answering our questions. And
thanks a lot for the invitation, all the attention you gave me, and these very insightful questions that allowed me to, you know, make an even better point. Thanks a lot.
Great, thanks a lot. I'll invite you from the stage, and then but that doesn't work. I don't see why not. Okay, this also concludes this session. So I'm going to click on take a break. That means that in half an hour, we'll be back for the final session of the Haskell Symposium. If you want, you can go to the lounge and talk to other people at the tables reserved for the Haskell Symposium. Please do. And I hope to see you there. Goodbye.